All right. All right. Good morning, everybody. So, let's see here. All right, I'm gonna close this up, and I'm just gonna start sharing my screen here. Okay. Okay, everybody. So, as I mentioned before, I don't usually keep track of the chat messages. So if anybody has a question, just ask it. And so this is mainly a message for the people that are online right now. And as I mentioned to the people that are here right now, we're going to start today with we're going to work on a homework problem. We're going to work on problem 136. And let me just get this. Okay, let's start right here. Just a minute. Also, if you haven't done so already, go ahead and log into your iClicker app. We'll be using it today. And we will be going over parts of chapter 2. As soon as I get access here. Just bear with me. Oh, that's a bummer. All right, so yeah, it's just that. So the reason I'm a little bit slow right now is because my computer actually shut down all the way, so I don't have a copy of that problem. So as I mentioned, I wanted to start off class today talking about problem 136 from the homework, and because it's one that a lot of people have had issues with. And I guess let me just make a quick statement. I know that a lot of you guys, well, some students in class right now are still struggling with obtaining access to Pearson for whatever reason. Sometimes it's not following the directions. Sometimes it's a legitimate issue with either the UTEP side or the Pearson side. So, and it's not that many people, maybe 5 people more or less that are still trying to set it up. Chapter 1 homework is due today, but if you're still having issues in gaining access, just make sure you let me know, and I'm willing to extend the deadline for this week until this Sunday, okay, for chapter 1, if you're struggling. But if you've already set up an account and you've taken a look at it, then I'm expecting it to be submitted today, unless there's an issue. The other thing that I was gonna mention, I guess that's mainly it. For chapter 2, I'll be assigning it, if not today, then tomorrow, and so you guys can at least take a look at it. We're gonna be going over chapter 2 today, as well as next lecture. So if you look at the homework and don't recognize a lot of the stuff, don't worry too much. We'll cover some of it. But it's still a good time to start looking at it so you can ask questions about it. Are there any questions about that? Anybody? Okay. So yeah, let's go ahead and work on chapter 1 of problem 136. Now, unfortunately, I don't have a copy of the problem, just kind of what I worked on in my last class here. So, I mean, I kind of remember what it's about, so we'll do it here. Let me just set something up here in my settings, and then we'll get started. Okay. Hopefully. Okay. Hopefully that's better. All right. So in this problem, we had a person. What was her name? You guys remember? Okay, let's just call her Rosa for today. She's gonna travel um, south along some street. Do you guys remember the name of the street? Just got Street 1. Okay. And I'm gonna just kind of start drawing it out from. So basically, the problem means you start off at some initial place, and it's gonna travel along the south until the intersection with, I think it was Broadway, maybe. Let's just call this Broadway Street. And then once they get to that point, so and then there's a distance that they traveled. So the south along Street 1 toward intersection. And this was a distance. Everybody's going to have a different number, but I'm going to call this D1, and I'm going to say that that's equal to, I think 0.8 was one of the numbers, miles. Okay, so we'll have D1 right here is where they went, and then it says they're going to turn east until Broadway turns. So in that problem, Broadway Street at some point has this kind of turns up at some angle. It says it's like a 30-degree angle. All right. And so, and then it tells you another distance. So we're going to call the distance down here D2. And for this problem, let's make D2 equal to 0.9 miles. And then finally, so start off here, go towards the intersection. 1, 2, and then step 3 was you're going to travel or keep traveling on Broadway for 1.6 miles. Okay, so I just made this problem very everything's cluttered in one spot. But the idea is, so if I kind of draw it again, basically we go down D1, gonna go over D2, and then after we pass that D2, we're gonna travel this extra distance that I'm gonna call D3, and that D3 is equal to 1.6 miles, okay? And it's making this angle of 30 degrees, all right? So that's the situation we've got right now. And the problem asks in the first part is to find the magnitude of the displacement. So magnitude of displacement, usually we'll use these double lines and then the vector for displacement on the inside. And then part B asks for the direction of the displacement. Okay. So that's kind of the setup. And if you haven't seen that problem, I suggest you go and actually look at the pretty drawing in the description. So I'm going to go ahead and just draw it again, just for making things a little bit more clear. So we have this distance d1. We're going to travel east, the distance d2. And at that point, we're going to travel upward along this diagonal distance of d3. And so what we're trying to find out is for A is magnitude of the displacement and direction of this displacement, okay? So in this cartoon, at the end of the day, we're gonna, really what we're discussing is a vector that goes from the starting point, you know, up here, till the point where she finally gets to the store, which is there. So the total displacement vector is gonna be this vector that goes from the start to the end, kind of like that. So that's the vector D that we're looking for, okay? And so, let me see if I can make this a little bit bigger. Okay, so if you remember our discussions about vectors, really what we're doing is you got to think about this distance D1, D2, and D3. Think of those as individual vectors. So D1 is actually a vector that goes downward. D2 is a vector that goes to the east. And D3 is a vector that goes along that street in that direction. So the first thing that we want to do is we want to make sure we all agree on the coordinate system. So if we make up north, obviously down will be south, to the right will be east, to the left will be west. In Cartesian space, north, that's going to be our plus y direction, and east will be our plus x direction. All right. So, and at the end of the day, what we have is a problem where we have vector D, which is the one we're looking for. It's just built from all the different displacement vectors, right? So the D that we're looking for is equal to D1 plus the vector D2 plus the vector D3, right? That's going to give us the answer. One of the things we mentioned in class before was anytime you see a vector sum, like the one that I've written there, and you're dealing with motion on at least two dimensions. So right now we have two dimensions, right? We're going north-south is one direction along the y, and east-west is the other direction, right? That's the plus x minus x. So anytime you see an expression like what I've written there, you always you have to really realize that this is really giving you two equations. They're giving you an equation for d in the x and an equation for d in the y. D in the x is going to be, well, whatever component of d1 exists that's in the x direction, plus the component of d2 in the x direction, plus the component of d3 in the x direction. And then for y, it's going to be, similarly, d1 in the y plus d2 components in the y direction, plus the d3 components in the y direction. All right. And so then you look at your problem and you say, okay, well, is there actually going to be a value for each one of these expressions that I've written there? Well, when you look at your problem, we can say that, for example, with D1, it's all in the y, right? So D1 actually equals D1 in the y. And the component of D1 in the x, well, that's just zero. There's nothing there. So we get to simplify our expression that way. So when you look at this, D1 in the x, well, we can just kind of cross that out, ignore it. Same thing when you look at D2, you find that, well, D2, it's all in the x. So D2, all of it is actually D2x. And D2 in the y doesn't exist, it's zero. So in this expression, D2 in the y gets crossed out, okay? So far, we're starting to get somewhere, right? Now, the question now is, well, what about all the other ones? So let's look at D2 and the X first. D2 and the X, if you remember from the initial setup, I think I had said this was going to be equal to 0.9. And I think I said D1 was 0.8 maybe. So D2 and the X, which is the one here, that's going to equal, and I'm going to go ahead and put a positive sign because it's to the right in the positive X direction, 0.9 miles. And then you start seeing things like these D3X, D3Y components. So another thing that you have to, part of the process here is to realize that, well, even that D3, because it's diagonal, it's composed of two other vectors. So this D3, I'm going to draw it here on the side. That's that same D3 that we have in the problem. Well, you have to imagine that you can get D3 by adding an X component, which we can call D3X, plus a Y component that we can call D3Y. And those two components are always going to be perpendicular, okay? And so now that we've got this angle, this D3 in the problem, I think for everybody it's a 30-degree angle. And so this D3 vector is at 30 degrees with respect to the components. So this is the part where we're going to use a little bit of our knowledge of geometry and trig to say, okay, well, we can use the sine and cosine functions, right? So we use sine of 30 degrees. That's going to be opposite over our hypotenuse. So that's D3y over D3. You can solve that for D3y, and you're going to get that D3y is equal to D3 times sine of 30. And you can keep adding all the information there. So we know D3 had a distance of 1.6 miles. So in this part, D3y is going to be 1.6 miles times the sine of 30. That's going to give you one answer. Similarly, you could do the same thing for the other component using the cosine function. And if somebody can calculate that and tell me the answer, please share. I think it should be 2.1 something, 1.2 maybe, but I'll wait for you. But yeah, so if we look at the cosine function, and I'll do it up here. Cosine of 30 degrees, that's adjacent over hypotenuse. Put a little arrow there. So that's going to be D3x over D3. And similarly, you'll be able to write that D3 is equal to D3x is equal to D3 times the cosine of 30. So for this one, D3x is going to be 1.6 times the cosine of 30. And I know it's kind of looking jumbled there, so I'll stop scribbling there. So the goal is to calculate 1.6 times sine of 30 for D3y. Did somebody get what that one should be? Okay, you're probably using radians. Anybody? So 1.6 times the sine of 30? Okay. I guess that makes sense. Does that make sense?
When you find the cosine of 1.6 cosine of 30, I got 1.4.
Okay. Okay. So tell me again what D3y was? 0.8 something? 0.8. Okay. And then D3x. Okay. So I'm going to take this right here and let's take it all the way down here. D3x was 1.4 miles for both of those. Okay. So we have the D3x, we have the D3y, and that's what's going to be, those are the values that are going to go into those expressions that you see into the x and the y expressions, all right? So that's kind of like a whole step, right? Is just breaking down that diagonal vector. All right. So now going back to our full equation here, let's continue this expression that I had for the dx's. So these guys right here, then we're gonna have dx is, so we crossed out d1x, so now it's just d2x, which we said is that 0.9 miles. That is from this part right here. All right, that's how that got in there. And then plus d3x, which we obtained from, you guys just found, which is 1.9 miles. So if you add up those, you're gonna get what, 2.3 miles, right? Now for dy, that's gonna be d1 in the y. So d1, we said all of it was pointing down, right? One thing that we have to be careful about though is remembering that these things are vectors. And so d1 in the y direction, because it's pointing down, it's gonna have a negative value associated with it. So this guy right here is actually minus 0.8 miles, okay? So when you write down for dy that it's d1y, well, it's gonna be negative 0.8 miles plus, we canceled d2y, so now we got d3y, and you guys found a value of 0.8 for that one. And I just magically happened to choose the numbers where dy actually canceled and made it, so that's a 0. So in this particular solution, we only have motion in the x direction. And so for this problem, I'm kind of upset that I picked that value. Let's okay, I hate doing this because it screws up your thinking a little bit, but what if this value of d1 was not exactly 0.8, so that it cancels out exactly? What if that value was a little bit larger? Let's say it was 1 mile. And this could very well be the case for many people in the class, right? Because those numbers are going to vary. So I'm going to take this liberty here to mess with you guys a little bit, but I think it's worth it. So right here, let's just say I change this to 1 mile, okay? Just because it illustrates the example better. So d1y now is negative 1 mile, okay? And so when you go through this step to fill everything in, this dy, this is actually negative 1 mile now, okay? So when you do that, negative 1 plus 0.8, that gives you negative 0.2 miles, okay? And there's a reason I wanted to do this, because I wanted to have both x and y components so we can continue with the example. So far, we've gotten to the point where we know the value of the components dx and dy. So we got 2.3 in the positive x and negative 0.2 in the y, okay? So let's, I'm gonna rewrite those again real quick here. So dx, I think I am. dx we said was 2.3 and dy was negative 0. What did I say, 2?
Yes.
Right, okay. So, so if we were to plot that, we would say, okay, well, we're gonna start here. Here's our starting point. This is where we start off at. And so we're saying we're gonna move 2.3 to the right to draw this vector. If I can get my mouse to cooperate here. So that's dx, 2.3. And then we're gonna go negative 0.2 for dy. All right, this is in miles. All right, and so this is, and so the sum of those two, we said, is gonna give us our final vector d. So our goal in terms of finding the magnitude is going to be that d, which we had said is dx plus dy. To get the magnitude, we're going to use Pythagorean theorem. So in this case, we know the size, the absolute value, is going to be given by d squared is equal to dx squared plus dy squared. So that means that d is going to be given by the square root of, so dx is 2.3 squared plus dy was 0.2. And you can put it negative, but it'll make it positive when you square it. And so that's what we're going to use to find the magnitude d. Can somebody do that and tell me the answer? So essentially whatever number comes out of here is what the displacement is going to be. That's going to be part A. Okay. And if somebody gets it, just tell me and I'll write it down. So you still get 2.3 something, just, yeah, so if you round it out, it'll still be close to 2.3. It depends on whatever the digits are here. But this is an interesting example because it's mainly because that 0.2 is really small. If instead of negative 0.2, it was like -1, then that would be a triangle with pretty long sides. And so your answer wouldn't be exactly or very similar to that 2.3, okay? But that's going to be what gives you the answer for the magnitude. Now the next part has to do with the angle. And right now we're talking about this angle. We'll call this, we'll just call it theta as well. And one thing that maybe I didn't emphasize too much is in this class, we know that in terms of directions, we have north, south, west, east. So in this case, we could say it's going to be some angle theta, some degrees, some angle in degrees, south of east, right? Because it's kind of pointing downward and a little bit diagonal. Another way of reporting direction has to do with the convention that, so we can also do it this way, where when you have your Cartesian coordinates, if you go from this positive x direction and you go, counterclockwise, this would give you a positive angle. So if you're doing counterclockwise, it's a positive theta. If you're going clockwise, so instead of going up, you're going now down from that x-axis, then in this case, that would be a negative angle theta, okay? So, and in the homework, they're kind of expecting you to put the answer in either positive or negative angle. And so realistically for our case, because we're pointing kind of downward, if I were to redraw our axis, we kind of looks like that. You're going to have two options. You're going to either report it in terms of this angle, which will be a negative angle, or you're going to report your answer as a positive angle, but it's an angle that goes all the way around to that point. So in this case, another option is you could say theta is equal to 360 minus whatever that small angle is that you've got there, okay? And so that's the approach. And so what we're going to do then is, well, let's find the angle. And so in our case, the easiest thing to use is to use a tangent function. Since we have the opposite and the adjacent, those are like the original values. So we can say tangent of theta. So using opposite over adjacent, that's going to be dy over dx. And the magnitudes of those are 0.2 over 2.3. So then at the end, your angle theta is going to be the inverse tangent of 0.2 over 2.3. And that'll give you it should be a pretty small angle. Anybody calculate it by chance, or can somebody calculate it? And like I said, these are all kind of made up numbers, but the equations are kind of what you need to help solve the problem. So from this example, anybody get a number yet? Dun, dun, dun. This is tests on how to use calculators, right? You gotta, so it's either tangent to the -1 or like the a tan function in some calculators. 4 point what? Okay, so let's just say you got 4.87. So in this case, theta would be negative 4.87, and that would be a number that should be accepted in the software. Or you do 360 minus 4.87, and that big number then is, you enter that as a positive answer. Any questions? People online? Everybody okay? All right.
We're good.
Yes.
No, I'm saying we're good. Answering
Oh.
your question.
Okay, you're good. All right, that guy just spoke for everybody online. So let's hope you're good. All right, so anyway, that was problem 136. So we found the magnitude and the angle, which gives you direction. So I'm gonna now go ahead and move on to the main topic for today, which is to continue in chapter 2. So this is chapter 2. We'll call this part 2 for today. And as a little bit of review, some of the critical things that we've talked about so far are displacement, right? We know that displacement is given by the difference in the final minus between the final and the initial displacement vectors. We also discussed that with uniform motion, this is motion that is in a straight line, and it's also motion that has a constant velocity. In those cases, we get an expression that says that velocity is equal to, so if we're looking in the x direction, it'll be Vx is equal to delta x over delta time. And because it's constant, that velocity is a constant term. So you could rearrange this to solve for x. So it could be delta x is equal to Vx times delta time. You could even use it to solve for time. If they gave you the velocity and the distance traveled, you'd be like, oh, it took them 20 minutes to get there, I know it. And so if you want to do that kind of a problem, then you'd have to rearrange it and have it so that delta time is equal to delta x divided by Vx, all right? So we're going to use that information for this problem that says, so if we read it, it says a train moving due west at a constant speed. A passenger notes that it takes 10 minutes to travel 12 kilometers. How long will it take the train to travel 60 kilometers? And so there's two ways of solving this. One of them is using all these equations. The other one is a little bit more intuitive because we know he's moving at a constant speed, right? So we know that if it takes a time of 10 minutes to travel a distance of 12 kilometers, so this is your x of 12. I mean, you could do a kind of quick one to say, well, how far will he go? He goes for 20 minutes, right? Twice the distance, twice the time. Well, that's going to be 24 kilometers, right? Or if I tell you he traveled 36 kilometers and you already know that it took him 10 minutes to do 12, well, you know that 12 goes into 36 3 times. So it must be 3 times longer. So in this case, it would be 30 minutes. And so one way of analyzing this problem is to say, okay, well, and I shouldn't have drawn that squiggly line, but get rid of that. So we know that 60 kilometers versus 10 kilometers, or 12, I'm sorry. If you do 60 over 12, we know that that's 5 times further, right? So that means it should take 5 times longer. Take 5 times longer. So that's one strategy. And this only applies when you're moving at a constant velocity. So in that case, if it's going to be 5 times further, it's going to take 5 times longer. So from here, you could say, so it'll take 10 minutes times 5 is 50 minutes. And you're done. Okay. Now, the other way you could do this is you could use all these algebraic expressions that I just wrote here. This is another way of doing it. You could use the starting conditions or the starting info to calculate Vx. In this case, the velocity V in the x would be given by the distance, which was 12 kilometers, divided by the time, which was 10 minutes. So here you would get 1.2 kilometers per minute. And then what you could do is to say, okay, well now you're gonna apply to the 60 km problem. And so in that case, what you're gonna do is you're gonna find that the goal is to find the time. So find delta t by doing delta x over Vx, which is that equation I wrote down earlier. And so here you would put delta x was 60 kilometers divided by the velocity, which was 1.2 kilometers per minute. And you find that when you do 60 divided by 1.2, that's also going to give you 50 minutes. Okay. So those are kind of two ways of doing it. Like I said, when you're moving at a constant velocity, you can just quickly do those ratios and you'll get there a lot faster. So, and they did it on purpose to tell you that, well, 60 divided by 12 is exactly 5. So then you just multiply your 5 times the original time for the shorter trip. Does that make sense? So we'll do I don't know how many of these we'll do, but this is a good strategy whenever you're dealing with constant velocity problems. All right. So, and if something doesn't sit well with you yet here, just go ahead and sorry, I'm just checking to make sure I'm recording. Yeah, go back and look at the slides and let me know if you have any questions. All right. All right. So we're next going to look at some more properties of graphs. And as a little bit of review from previously, we know that when we have a position versus time graph, what does the slope give you? Anybody? Yeah, slope gives you velocity. So if you got a little graph, it looks like this, and position's always going to be like something in units of meters, and time, oftentimes we'll use seconds. Yeah, what we're talking about is the slope, rise over run. That thing is what gives you the velocity. Okay. What we're going to focus on right now is, well, what happens? So it turns out that there's another relationship. So this was for position versus time. But if we want to look at velocity versus time, in a velocity versus time graph, we're going to find that the area under the curve over a given time interval gives displacement. So that's the big thing, is area under the curve gives you displacement. And so in this problem, and you always want to look at units to see if things kind of make sense. In the case of position and time, well, slope if you remember, was given by rise over run. So the units in this case were meters divided by seconds. So it's units of meters per second, or it could have been miles per hour, right? So we know that's a speed, it makes sense. Similarly, with a velocity versus time graph, you want to do the same kind of, so this is called dimensional analysis, where you say, okay, well, in a velocity versus time graph, we are in units of velocity that are in meters per second, and our time is in units of seconds. So we're doing an area. Well, area, you know, let's say in this problem, we had a motion, a velocity graph that looks kind of like this, like what they've shown in the slide there. Well, in this case, this area, which is length times width, well, we have to ask the question, well, what's the time interval? And this problem, they're looking at a time interval between 1 second and 3 seconds. So that's how we define that part. So the base or the width of your little rectangle is this part here. That's the delta t, which is 2 seconds. And then the height of this rectangle would be the velocity, which in this problem is Vx is equal to 12 meters per second. So if you want to find the area is going to be the velocity in the x is the height, and then the base is going to be the delta t. And so for this problem, it's going to be 12 meters per second times 2 seconds. And one of the things that you'll notice is the seconds cancel out, and you're left with an answer that's only in meters, which is good, right? We have the right units. We're looking for units of length for displacement. And so 12 times 2 is going to give you 24 meters for the answer. Okay? And so it's a cool relationship that the area gives you the displacement. And so if we were to do a problem like this one here, let's see if we can get it. So here in Quick Check 2.8, it says, so they're showing us a velocity of an object that is at the origin at x equals 0 and time equals 0. So when you start the watch, it's just at the origin. And then you see the velocity profile. You can tell that it moves at 4 meters per second for the first 2 seconds. And then after those 2 seconds, it's going to start slowing down for the next 2 seconds, from 2 to 4 seconds, until it reaches a velocity of 0 by the time we get to 4 seconds. And so, but what we're going to do is we're going to make use of the fact that the area under this curve is going to give us the displacement. All right. So let's go ahead and draw that problem out. So we're going to have here, looks like this. We have, so remember this is velocity. So right away, you know, we're going to be able to get the area. And really it's 2 shapes, right? We got this rectangular-like shape, and then we got this triangular kind of shape here. And it takes a turn, like I said, at 2 seconds, and then it gets to 0 by the time we get to 4 seconds. Originally, it was at 4 meters per second. So really, to get the displacement, which is equal to the area, what's going to be area 1 of this rectangular shape or square plus area 2. So the displacement is going to be A1 plus A2. A1 was given by, so we have this part here, that's delta t equal to 2. And then the height was 4. So we'll have 4 meters per second times 2 seconds. That's going to give us 8, right, meters. But we're doing a second area. So A2 is this part here. And A2 is this triangle. So for A2, area of a triangle, we know is 1/2 base times height, right? So, hold on, let me re-enable my little thing here. So we know the expression for a triangle is 1/2 base times height. So it's going to be 1/2. The base of this is, once again, the time interval. So now we're from 2 to 4 seconds. That's also a delta t of 2. So it's 1/2 times 2 seconds. And the height is the height of this triangle. So that right there, that height is also 4 meters per second. So we'll put 4 meters per second in there. So if you take 1/2 times 2 is just 1, and then 1 times 4 gives you 4. So that gives you area 2 of 4. So let me just rewrite this. 1/2 times 2 times 4 gives you 4 meters. So that's why you get this value of 12 meters for your answer, which is what most people finally kind of got now. Any questions about that? So that's going to be one strategy when you're given a problem where you have pretty shapes like triangles and squares. Right away, just think your geometry stuff, and hopefully you remember the areas of those kinds of shapes. But I think for the most part, it'll be squares and triangles, maybe some like half circles in some cases, but it won't be too crazy beyond that. Okay, so far we've talked, everything we've talked about, it all works nicely when you've got constant velocity, when you've got, uniform motion and it's not changing. Velocity is the same at the beginning as it was at some later time and everywhere in between. What we're going to talk about now is this idea of instantaneous velocity. So this is a velocity as you might think of at a given instant in time. And so what they are graphing in that plot here on the slide is a situation where the velocity is changing. So if we're looking at a position versus time graph, and we know that slope is the velocity, well, what they're saying is when you first start out, you might have, 1 point here, you go another equal time interval, maybe it goes up a little bit, another equal time interval, all of a sudden you see it starting to really pick up now. And so another equal time interval, now we're covering more and more space, more and more of this x distance. And then the next time interval, all of a sudden you see it like, whoa, it's really jumping now. And you can keep doing this and to see how high it goes. And so we're now kind of plotting a curved trajectory, right? It's not the straight lines you guys are used to. And so the question is, okay, well, how does our analysis change in this case? Because in this case, I'm telling you the velocity is increasing. And we know this because when we look at these different time intervals at the very beginning, we might have let's say that we focus on this time interval, just as an example. Well, in this case, we're going to have a little delta t, that's that distance. And at the same time, there's matching x coordinates. So we have an x coordinate here, another x coordinate there. And so really our delta x is kind of small, right? We're not covering very large distance. You can go later to another equally sized time interval like I did here. So once again, we still have the same delta t, but now the matching points are going to be, this x point up here and this x point way up there. And so now our delta x is much larger, right? At the beginning of time on this graph, we had a small delta x. Now for the same time interval, we have a much larger delta x. And obviously that goes with the matching slope. And so the idea here is, we've been accustomed to just drawing lines through those points, right? That line that we use to draw between those 2 points, that gives you the average velocity in that interval, okay? The idea with this instantaneous velocity, what we want to do in that case is we want to zoom in and shrink delta t. And this is the part where if you want to do this like extremely correctly, you would resort to the calculus aspect of this. Basically, the zooming in bit of going in and looking at a really small time interval is what is known as taking the limits as delta t approaches 0. So as you go to really small intervals, you look closer and closer, and it turns out that if you zoom in to any curved shape, eventually you zoom in enough that it looks nice and flat. And I'm sure you've had this experience in math classes where you've got your graphing calculator. If your X window is really wide, you can see the whole curve, like if it's a parabola, but you zoom in, it's always going to look like a line, right? It's either going to point up or point down. And that's kind of the idea behind instantaneous velocity, that As you zoom in, everything looks like a straight line, and you can still apply the same slope formula, the rise over run stuff. So because of that, of those relationships, basically what that means is if you start off with a graph that maybe looks like that. Oh, I don't like that one. Hold on. So if you start off with something that looks like this, and you say, okay, well, maybe I'm interested in the velocity at this instant in time. So I want to know at this time, we'll call that t0 for whatever reason. So the goal in this case is find velocity at t0. Well, if you start off zoomed like pretty far away, so let's say we pick points that are kind of far out here. Well, in that case, the best we can do is we subtract the final from the initial and you get the slope, and it's going to be a line that kind of looks like that, right? So it's kind of an approximation. It's not going to be very good. But as you pick smaller and smaller increments in time, so let's say instead now I pick points that are a little closer to the time, maybe here. Well, now we're getting a little better, but you're still making a line that goes between 2 points. So instantaneous velocity is going to be given by what's known as the tangent line at that point. So let me write that down and then we'll talk about it. So instantaneous velocity is going to be given by the slope of the tangent line at a given point. And this is a point that we're interested in. So what is this business of tangent line? So tangent line is going to touches the plot or the graph or the data. I'll just put the curve at exactly 1 point. Okay, so I'll kind of isolate this from the rest of all my writing. So it's a line that touches at exactly 1 point. So you can imagine as we keep getting those points closer and closer to the point of interest, eventually we're going to have a line that it just looks like it's touching 1 point. And mathematically, you can make it touch exactly 1 point. So at this point, if we keep zooming in, these points will be right around that point of interest. And so we're going to have this line right here that we'll call the tangent line. So it touches 1 point. That's the key thing. And like I said, the slope tells you what the velocity is. And so the reason I'm explaining all this is because you might have problems where they might tell you the properties of a tangent line, and then you'll be expected to say, okay, well, if I know the slope of this tangent line, I automatically know the velocity in my problem that I've been given, and then you can kind of continue solving it. And it turns out that as you get closer and closer to that point and you use new points, you get more and more close to the true instantaneous velocity. And some of you guys might have cars that actually calculate this for you. If you ever look at any car that's maybe like 10 years, no more than 10 years old or even 20 years old, sometimes there's settings that tells you what your average speed is or your instantaneous speed. The average speed is the one that calculates, let's say you go and you drive to the store and back. It might say your average speed was like 10 miles an hour or 15 miles an hour. Even though you were going 35 at one point, maybe you sped up to 50, maybe you were at a stop sign, but it adds up all those velocities and gives you the average. What you see on the speedometer when you're actually driving, that's more like the instantaneous one, that one that actually changes if you step on the gas or put on the brake, right? So that's a real quantity. Now, it turns out that this business of getting the area under the velocity curve, it's going to give you the displacement in every situation, even if it's not uniform motion. So that's kind of a cool property. So in this case, when you see that graph, even though it's a curved velocity graph, If you can find a way to get the area under that curve, it's, you're always going to get exactly what the displacement is. Okay. Um, I'm actually gonna, so, and this applies, and so remembering that these things are vector quantities and the positives and negatives match, you might have a situation where, so let's just call this area under velocity versus time graph gives, so area gives displacement. So I mean, you won't have to do too many of these problems in class, but let's just suppose that you had a velocity versus time graph that looked kind of crazy, where maybe it kind of starts off up here and then actually dips down to a negative value and it comes back up. And let's say that I tell you that let's call this area 1 and let's call this area 2. If I tell you that area 1 is 2 times bigger than area 2, so basically it takes 2 of area 2's to make area 1, well, you're still going to do the same thing. So down here, area 1, this will be a positive value. This area, because it's below the axis, this would be a negative area. And so when you add these, and in this case, basically the total displacement is going to be area 1 minus area 2, because it's area 2 is below the v equals 0 line. But let's kind of move on from that, because maybe we need to do a few practice problems before we think about other stuff like that. So this quick check is just to see if you guys have been listening to what I've said a few times. So it says here the slope at a point on a position versus time graph of an object. What does it give you? Speed, velocity, acceleration, distance? Not sure. So slope on a position versus time graph. All right, so lots of B's, and indeed it is B. So remember, you had the option of picking speed, but it turns out, as we mentioned last time, when you've got position versus time, because we're looking at the slope, you can have a negative slope. In this case, negative slope means you've got negative velocity. So the signs tell you about direction. So yeah, indeed, it does give you velocity. It's not just magnitude, but also the sign gives you direction. Okay. So here's another problem. So in this problem, it says, when do objects 1 and 2 have the same velocity? And so you take this graph, so this is going to be quick check 2, 10. You see this, and then you've got 1 that goes like that. That's going to be number 2, and then number 1 has this business. And it looks like they intersect at some point in between or here, and that's called T0 versus time. Got a lot of responses already. Ooh, now we got A's and B's. So this is interesting because I started drawing everything. One of the first things you should do when you look at these graphs is, okay, they're asking about when do they have the same velocity. But the question is, what kind of graph are we looking at? Is it a velocity versus time graph? Or is it position versus time graph? Because if they're asking about velocity and it's a velocity graph, then obviously it's going to be the place where the two match, right? They're going to be like, oh, it's at this point they cross it, they have the same value, you're done. But if you look closely, and I don't know if they do this on purpose or not, but that graph it's not velocity, right? It's position. This is X. And so because it's position and they're asking about velocity, then what are we looking for? We're looking for the place where the slopes are the ones that match, not the points themselves, okay? And so in this graph, let's see if people are, oh, it's still split. I like it when it's split. So, so, okay, so the goal here is we're gonna look at slopes. So for this position graph, we're gonna look for identical slopes to find identical v, identical velocity. So in this case, if you start, I mean, so we know, for example, object number 2 has exactly the same velocity at all points, right? So that's nothing to worry about. Down here, same slope, that's not changing at all, okay? But if we look at the slope for object number 1, at the very beginning, well, it's got a crazy slope, right? It's super steep. So we know that's not the same velocity. As you keep going forward, the velocity decreases. And you can tell there's places now, here, this middle one that I've drawn, it kind of looks like it's parallel to the one for 2. So right there gives you a hint. Oh, okay, right there, that little instant in time, the instantaneous velocity is the same because they have the same slope. So basically what I've drawn here is like a little tangent line, right? That's nice and parallel to number 2. If you keep going, you'll see the slope gets smaller, it gets more shallow. At the place where they intersect, well, you got one slope versus the other slope of number 2, so that's different velocities. And if you keep going past t0, it basically looks like it's really low, almost 0. So those velocities are never going to be the same. So all we know for sure is somewhere in this region, and before 2 is where you get the same velocity. So we can say same velocity. And it's really vague, right? It's at some instant, not at the very beginning, but it's somewhere in there, some instant before t0. Okay. And so for this problem, yeah, the correct answer is A, some instant before t0. So everyone that had chosen at t0, if this had been the velocity graph, you would have been right, but it's position graph, okay? And that's going to be one of the places where people falter a lot. So anytime you look at homework, make sure you read those axes. Even if you ever do like research or anything, related to science or medicine, it's important to know how to read graphs. It's like critical. And I've had, so in my position where I teach students and they present and they show results and data, one of the pet peeves of people in my position to look at a graph is to say, hey, well, you didn't even label your axes. Like, and this happens like when you plot it on Excel, right? You just pick the columns, plot them, but you need to make sure if it's time, say it's time. And if it's in seconds, label it as seconds or hours, whatever it is. Y-axis, same thing. It might be distance, might be velocity. Later on, we're going to be looking at acceleration. We're even going to be looking at graphs with forces as a function of distance and time. So labeling graphs is important, and also reading them is also critical. All right. All right, here's another one, a little bit similar. So here they tell you masses P and Q move with position graphs shown. Do P and Q ever have the same velocity? And if so, at what time? So this problem is very similar in the sense that, once again, we're looking at position versus time. And once again, they're asking about velocity. So we've got one graph or one trajectory for P, looks like that. And for Q, we've got one where it crosses at 2 places and there's a little bulge looks like that. So you're going to do the same exact, we're going to use the same method we used last time to figure out what's the answer. So in this problem, I guess one main difference is that they actually labeled it with time points. So they, at this point, that happens at 1 second, 2 seconds, somewhere around here, and then the lines intersect at about 3 seconds. So in this case, you could say at 1 second, you could say it's the same position. That's fine. At time equal 3 seconds, it's also the same position. But because they're asking about velocity, once again, you have to look at the slopes. And so for particle or object Q, at the place where they intersect here, that's too steep. It gets less steep. At some point here in the middle, it looks kind of parallel to the straight line, and then it deviates. Here it's lower. So we're looking at some place in here where it's going to be the same velocity. And so in this case, we get that they're going to have the same velocity at t equal to 2 seconds. So roughly there at that region, you have two parallel lines, the line of trajectory p and then the tangent line of particle q. So q is going to have some kind of nice parallel line with p. All right. All right. Let's see. We got a little bit more time here. So let's do a slightly more applied problem with some numbers. And then I think after this, we'll call it a day and cover the rest next time. So it says here, the figure below shows a velocity versus time graph of a car pulling away from a stop. How far does a car move during the first 3 seconds? So we have to make sure we understand what they're asking for first. So they want to know how far. So right away, it's going to be some kind of delta x during, it says the first 3 seconds. So they're telling you the time interval is delta t is equal to 3 seconds. And because it's the first 3 seconds, really it's some final time minus an initial time. It's basically 3 seconds minus 0 seconds, right? I mean, just to be absolutely clear about it, right? That's what we're looking at. So when you go and look at the velocity versus time graph, you know, that's gonna look a little bit like this. So that's velocity, and we're using meters per second. And so starting off at time equals 0, and we're gonna go out to 3 seconds. We got this nice straight line trajectory. And so because we're looking at a velocity versus time graph, and they're asking for displacement, then we know that area of velocity versus time graph is going to give displacement. So in this problem, we've got this nice triangle, and we just have to calculate 1/2 base times height. So area 1/2 base times height. The base is going to be this distance here. That's our delta t, which is 3 seconds. And then so this is the area we're calculating, and the height is going to be whatever this reading is after 3 seconds. So if you look at your graph at 3 seconds, we're at about 12 meters per second. So in this case, it's going to be 1/2 times 3 seconds times the height, which is 12 meters per second. And so once again, the seconds cancel out. Your answer is going to be in meters. And so, you know, 1/2 times 3 times 12, that's going to give you 18 meters for the displacement. Okay. So any questions about that? Did somebody ask something online? Am I hearing things? Okay. All right, so this is another clear example of how you calculate displacement from a velocity graph. And you can see it was slowly speeding up based on what the graph is showing. We have a few minutes, so let's do a few more of these quick checks. Sorry, don't grab your stuff here. I'll let you go in a few minutes. So here's another one. It says here, a car moves along a straight stretch of road. The following graph shows the car's position as a function of time. At what point or points do the following conditions apply? So it might be, well, it might be hard to answer this one using that, so don't worry too much. But let's go ahead and actually analyze this step by step, and then I promise you guys can leave. So let's say we've got, I'm gonna just reproduce that graph here. So we're gonna go up and down and over. Okay. So we have, that's a really nice curve. I gotta give myself a pat in the back, guys. I make shitty drawings half the time. So positions A, B, C, D, and E is out here somewhere. Okay. So this is a graph of position. This is X versus time. First question is, when is displacement equal 0? So where would we say displacement 0? Is there a place? So remember, this is a graph of what? Position versus time, right? So we're just looking for places where position equals 0 in this first one. So in this case, the one where that happens is D, right? That's D is the only one that crosses, that goes to X equals 0. So for this one, get D. Next one, speed equals 0. Where do we get that? So in a position versus time graph, we know speed is like the magnitude of the velocity, right? So we're looking for places where the slope has a value of 0, right? If it's tilted in a positive direction, that's a positive velocity. Tilted downward, that's a negative velocity. But for 0 velocity or 0 speed, that means we need a straight line. Where do we get a straight slope? Well, in the graph, I think E is supposed to be flat. So in this case, I would say, yeah, you get a flat line at E. Anywhere else? Yeah, so at B, that's another place, right? Because we're going from upward to downward, right? So that there's a little magic place where it's going to be a 0 slope. And is that it? I think so, right? All right, next one is asking speed increasing. And I'll go ahead and write down speed decreasing already right here. So first one, for the speed increasing, which one would we say? Yeah, so this one's tricky because you might want to say A, because that is definitely the one with the steepest positive slope. But they're asking so they're not asking about the speed at that point. They're asking, is the speed increasing? Well, actually with A, even though at A it's nice and steep, a short moment after, it's gonna start getting more shallow, right? Because it's starting to go towards 0, right? Towards B. So C is one of those where it's negative, but it's still, we're asking about the magnitude, right? So speed is gonna, even though it's getting more and more negative as when you go from, so if you start at C and you go to the next point in time is gonna be even more steep. So that's even more negative velocity or an even higher speed, right? The magnitude is, is larger. So for that one, yeah, the speed is increasing at C. And by that same argument, you could say the speed is decreasing at A because, we just described it, right? It's the next time point is going to be more shallow. So in that case, that's kind of how that works out for that one. All right. And that's all I've got for today, guys. So what a weird schedule. So I'll see you guys next Wednesday, and everybody that's online that shows up, we'll see you Monday, and we'll continue from here. So thank you. Any questions?
Professor, can I talk to you? It's Mike Reyes.
Can you speak a little bit
Thank
louder,
you.
please? Thank you.
In reference to the homework, I had spoke to you the first day of class, letting you know that I was on orders.
Oh, right. Yeah. Can you remind me, what were the dates again?
I could send you the orders, but it was August 31st through September 11th, or the 12th is when I finish.
Yeah, I mean, I think like we spoke before, just shoot me an email real quick so that I have an official record, I guess, and then we'll deal with due dates on homework and stuff like that.
Okay, I'll send you this right now.
All right, sounds good. Thank you.
Thank you.
Okay,
Bye-bye.
bye. Yep.